Hello, everyone. We're continuing with our discussion of the weighted least squares approach. So we've been looking at the cases where we can model this heteroscedasticity up to a function, up to a multiplicative constant, meaning we can write this variance of, so we can write this variance of ui given xi as sigma square times h of x, or just sigma square times h sub I. And we've so far assumed that we know this h of x. We know we've been able to write this form for h of x. But oftentimes we don't know what it is. So what we're going to try and do in this segment is we're going to come up with an estimate of that h of x from our sample data. So we're going to replace that h of x with something that we can measure and compute from our sample. So we're actually going to get h hat and replace that, put that in place of h of I. So weighted least squares is a form of generalized least squares or GLS. Now, when you replace hi with h hat I, what you get is feasible generalized least squares or FGLS. So let's go ahead and see how we do that here. We're going to focus on a very specific case of this h hat. There are different ways in which we can do it in practice. We are going to learn of one specific way of handling it. Now, we start off by writing down the variance expression. Variance of u given x is just sigma square times h of x. And we're going to define a very particular functional form for this h of x. We're going to give it an exponential function. So h of x is just e raised to a particular linear combination of my x variables. And that's how I'm defining my h of x expression. And so if I plug that into my variance expression, I get this variance of u of x, u given x, is sigma square times this e power, a term of all your x variables. Now we're taking this particular exponential form for h of x because that way h of x is positive, and therefore variance of u given x is also always positive. So now we're going to figure out how to get this h of x from our data set. We're going to estimate this h of x from our sample, and that's how we're going to be able to come up with an expression for heteroscedasticity itself. So how do we estimate this h of x? Well, variance of u given x can be written down as expectation of u squared given x. Okay, we should know this by now. So I'm now going to rewrite this entire conditional variance of u given x by now having a u square term on my left-hand side. So I'll now say u square is sigma square times this h of x multiplied by another expression v. And this v is just, it's just a term which will have, that's immaterial for us at the moment. It just has a mean that is equal to unity conditional on all of our x variables. So if I were to just take the log versions of all of this entire term, so this v just has a conditional mean of 1. Okay. And why we include that v there will make sense in the next equation that you see. So if we were to just take a logarithmic transformation of this expression, we'll have log of u squared on the left-hand side, and then you'll have log of sigma square, and then you'll have a delta naught plus delta 1 x1 plus delta 2 x2 and so on up to delta k xk. And this log of v, I'm just going to call that e. So log of v, I'm just going to call that e. And this intercept is actually going to be log of sigma square plus delta naught. So, but what the intercept is actually doesn't matter to us. What ultimately matters is that we now have an expression. We can now actually run a regression of log of u square on all of my x variables. And this will actually form the basis of how I get to my h of x function. So to recap, we're trying to figure out how to get an expression for h of x, and we're going to estimate that from our sample. And we're going to do that by defining h of x to be an exponential function. And how are we getting at that? We're taking log of u square and regressing that on all of our x variables. So when we estimate this particular log model using WLS, we're going to get unbiased delta J coefficients. So let's stay there. We don't know what u square is because that's from the population. So we substitute with u hat square. So what do? U hat is nothing but the residuals that you get from regressing y on all of your x variables. So run the original regression, get your residuals, square them, and then take a log of that. Now you regress the log of u hat square on all the regressors in your model. And once you run this regression, get the predicted or the fitted values from this regression. And let us call that GI hat. So all the predicted dependent values, predicted log of u hat squares from this regression, we call that GI hat. And we take an exponent of that. Okay. So if you take exponent of GI hat, the result that you get is your HI hat. So remember, we started off by defining h of x to be e power delta naught plus delta 1 x1 and so on up to delta k xk. Now, this delta naught plus delta 1 x1 and so on, we have an estimate of that from, this from our log regression. So in order to get h, all that we have to do is take an exponent, we just have to do exponent of the predicted value of that log u hat square. So we just have to do exponent of GI hat, and that gives us our HI hat. And once you know HI hat, 1 over HI becomes the weight in our weighted least squares. Why does 1 over HI become the weight? Remember, when you're doing weighted least squares, you're just minimizing the sum of squared errors, right? In the transformed model. And that is nothing but your sum of squared errors from the original model divided by this HI. So that's where the weight comes from. So the weight is 1 over HI. So though the weight is 1 over HI in the transformed model, you divide throughout by square root of HI hat. And though it may seem a little overwhelming now, with practice, you'll be very seamlessly able to speak about this like I am doing right now. So this is your feasible generalized least squares. So you define a functional form for that h of x, and you get an estimate of that from your sample. And once you know what that h hat is, you now construct your weights. And when such weights, such h hat values, when you use them, you're running a feasible GLS model. And an FGLS is also consistent and asymptotically more efficient than OLS. So naturally, this method works better when you have a larger sample size. Now, so whenever there's heteroscedasticity in your model, this is quite an attractive alternative to OLS. So the steps here are first regress y on all the x values and get your u hats. Then get log of u hat square and regress them on all the x variables. And then you obtain the fitted values g hat. Now I can either regress u hat on all the x values, or I can also regress the u hat square on my predicted y hat and y hat square values. That's just an alternate way of doing this to get my fitted values. And once I have g hat, I just have to get e power g hat, and that's all that I need to get my h hat. And once I know h hat, I know the functional form of my heteroscedasticity. And 1 over h hat becomes my weights. So I just transform all the variables and divide them by 1 over square root of hi hat, including the intercept, and that gives me my feasible GLS model. So in order to check if we should use the OLS or the feasible GLS model, we use something called the Hausman test. But the mechanics of that is a little too advanced for the purposes of our course, so we're just going to skip that for now. We'll now see a very quick example using the FGLS model. So we're looking at the number of cigarettes that somebody is smoking per day as a function of their income, as a function of the price of cigarettes, the person's education, age, and whether they live in a state which has smoking restrictions in the residence. So if we run a regression OLS model as it is, and if we actually do a Bluch-Pagan test for heteroscedasticity, the p-value of that test is really, really tiny. So a low p-value is evidence against the null, where the null is actually homoscedasticity. So we are now rejecting the null and concluding that there is heteroscedasticity in the model. Now, before I show you the heteroscedasticity corrected results, look at the significance of these coefficients, right? The log of income, this variable is not statistically significant, meaning income doesn't have a significant role in how much cigarettes somebody is smoking. Then the price of cigarettes is also not significant. Whether the person lives in a restaurant with, in a state with smoking restrictions in the residence appears to be moderately significant, but that's how the results are initially. Now, if I run an FGLS model using the methods that we've just described, here are the results. Now, the coefficients are a little bit different compared to what we saw earlier. The income variable is now statistically significant. It wasn't earlier. Now, the coefficient on the price of cigarettes is also increased, although it still remains statistically insignificant. And the restaurant variable, the smoking restrictions variable appears to be significant now. So, and if you actually notice the errors that you're seeing, right? The OLS standard errors are given in the parentheses here. So you have 24.7, 5.77, and so on. In the next slide, we actually have errors which the parenthesis has WLS standard errors or FGLS standard errors. And by definition, FGLS is more efficient. So that will have smaller variances and smaller standard errors. And you can see that in this example. So it just means that all the other coefficients are more precisely estimated, and that without changing the general conclusion of the model. So it just has lower standard errors. So this is just an example showing how it is done in practice. Now, if our OLS and WLS coefficients are significantly different, it means we need to pay a little bit more attention because one of our models could be misspecified. But we're not going to go into that in detail. This is just to show you how the FGLS model is done in practice. So we've now reviewed, we now know what heteroscedasticity is, and we also know how to get around this problem. We know how to do robust standard errors. We also know how to do weighted least squares. So with weighted least squares, the challenge is that sometimes we don't know the functional forms. So there's always some level of arbitrariness. So if we were to just sum up the issues surrounding this weighted least squares, what happens if the way in which we assumed heteroscedasticity, what if we get that assumption wrong? Well, when we misspecify the form of heteroscedasticity, it is still going to be consistent. That's not going to be a problem. But I think when you misspecify the form of heteroscedasticity, well, we may be worried that our standard errors and test statistics are now going to become invalid. Well, in that case, one solution is to do WLS, but then run robust standard errors on the WLS model. So that way you're buffering yourself, you're protecting yourself against any heteroscedasticity issues. Now, the other consequence of getting this functional form wrong is that your WLS may be less efficient than OLS. You may get the efficiency part of, you may go wrong there. But nevertheless, I think it's better to still use a wrong form of heteroscedasticity than to not use anything at all. So in general, in practice, you often always see people automatically accounting for heteroscedasticity, whether or not it actually is there in the model. So the simplest way of getting around this is to just use robust standard errors. It just takes one extra line of command or one extra word in some software programs to do that. So that is generally followed as best practice. So this brings to a wrap the different ways we commonly use to tackle this problem. So there's just one tiny segment left in the chapter. So I'll cover that in the next video. See you there.